Hello, and welcome to this talk on prefix grammars. I'm Ashley Suchi, and I worked with Polyeth Narendran and Yu Zhang on this paper. We all worked together at the University of Albany in New York. Our motivation for this paper came after we were reading the Fraser-Page paper and the Ravi Kumar and Kwan unpublished works. I hope you enjoy this talk. We'll start out today by looking at some background materials. Then we'll look at our results for prefix grammars, and lastly, our future work. The first thing we want to talk about is the definition of a prefix grammar. We'll use the usual definition where we have the triple with sigma as the alphabet, S as the base strings, and P as the productions. A prefix grammar is a string rewriting system where we apply the productions only to the prefixes of strings. Let's look at an example. Here we have a prefix grammar with A and B as the alphabet, A is the base string, and two rules, A goes to B and B goes to AB. To get strings in the prefix grammar, we start with a base string, in this case A, and we apply productions, and in this case we're ending with the string ABB. Now let's look at the definition of a right linear grammar. Here we're given a tuple where n is the set of non-terminals, sigma is the set of terminals, r is the set of rules where all the non-terminal symbols appear to the right of the terminal symbols, and the start symbol s. Again, let's take an example. Here we have the set of non-terminals s, va, and vb, the set of terminals a and b, the set of rules here, and the start symbol s. To get strings in the grammar, we start with the start symbol and apply productions or rules, and in this case we end with the string ABB again. This right linear grammar is actually equivalent to the prefix grammar we saw before. In this talk, we'll be focusing on the right linear grammars that we can obtain from prefix grammars. Let's take a look at the algorithm that allows us to do this conversion. The algorithm was given by Fraser and Page and works as follows. We take a prefix grammar as an input, and our goal is to get an equivalent right linear grammar. We start by letting the set of non-terminal symbols in the right linear grammar be S, followed by a non-terminal for each left-hand side of the rules in the prefix grammar. Then we're going to add rules, where we add a new rule from S for each base string in the prefix grammar. And then we add a rule for each original rule in the prefix grammar, where we take the right-hand side as the prefix, followed by the non-terminal corresponding to the left-hand side. After we have the initialization, we're going to add new rules. We want to search for rules from S using rules already in the right linear grammar, where we get some beta I as a prefix. This corresponds to our non-terminals we created. Then we'll add rules where we take the non-terminal corresponding to the prefix as the left-hand side, and the suffix will become the right-hand side of the new rule. We'll keep doing this till we can't add any more rules. Here, I'm presenting an oversimplified version. We actually want to find the minimal derivations here, where as soon as we find the last symbol in beta I, we stop. Let's take an example to clarify. We'll start with our prefix grammar from before, and we'll do the initialization step. Here we set up our terminal symbols. Our start symbol will be S. Our non-terminals are S, followed by VA and VB, coming from our left-hand sides. And we'll take the initial set of rules as S goes to the base string A, and then BVA from the first rule, and ABVB from the second rule. Now we want to add new rules by searching for derivations where we have A as a prefix. If we consider the first rule, we have S goes to A, so we add the rule VA goes to epsilon. We continue searching for rules, and so in the next step we have A as a prefix again, and BVB as the suffix. So we add VA and the right-hand side becomes the suffix of the string that we derived. Now we have no more rules with A as a prefix, so we continue our search, now looking for prefixes with B. We have just one rule here to add, and that leads us to the final set R for this right linear grammar. Let's take a look at another prefix grammar so that we can see derivations where we have more than just a single step. We'll fast forward to after we've done the initialization and after we've added rules for the non-terminal VA. So now we're searching for strings with the prefix AAB, ABB. Here we need to apply more than just one rule, so we always start with rules from the start symbol S. In this case, we take AAB, VA, which gives us the first part of the string. Then we can apply any of the rules that we added for the non-terminal VA. And so we'll apply these two rules, and at the end we've derived this whole string, and so we can go ahead and add the rule VAAB, ABB goes to epsilon. Again, we're going to search for any rules we can find, and so we have this other derivation with the last step being different, and so we can add this other rule to R, and again obtain our final set R. Now our next question is, what is the complexity of this conversion? And so we'll start by looking at the size of the final right linear grammar we obtain. If we remember, the algorithm starts by getting the initial grammar, and that size can be no more than the original size of the prefix grammar. Then we add new rules. If we remember, we add new rules in this format, and WV beta J has to be a suffix of a right-hand rule already in the grammar. So this tells us that we can add no more than M, which is the number of rules in the prefix grammar, times the initial size of the grammar we start with. And so the size of a right linear grammar has an order of the initial right linear grammar cubed. Now we want to see how long does it take to find a new rule. If we remember, to find a new rule, we're searching for a derivation of this form. So, thanks to Hopcroft, Motwani, and Ullman, we can check if a string X is in the language of a right linear grammar in order the size of the string times the size of our grammar squared. So we can plug in the string we're searching for and get our time. If we consider what is the longest length of these type strings, we have a weak upper bound of the size of the prefix grammar. Lastly, we want to say how many iterations or how many times do we have to do this steps. And so we'll consider the worst case where we have only one new rule each time. And so if we recall, the maximum number of rules was M times the initial right linear grammar. And so that is how many derivations we may have to do each iteration. It's also the maximum number of iterations we may have to do. This leads to the overall complexity of the order, the size of the prefix grammar to the 11th power, which seems very large, but is still polynomial time. The next thing we looked at was the equivalence of the prefix grammar and the right linear grammar that we obtain. And so here in part A, what we're saying is we're checking that the prefix grammar is a subset of the right linear grammar, and in B, we're checking the converse. Up next, we're going to talk about our results for prefix grammars. The first problem we're going to take a look at is the universality problem. We'll start with refreshing on some definitions. A and B are going to be sets over the alphabet sigma. The set A will be given as a set of strings x through xm. The set B will be a set of strings y1 through yn, where none of them are the empty string. We'll say that A and B cover a language if and only if L is a subset of A union B sigma star. We'll refresh on the definition of a left quotient. where when we take the left quotient with a string and a language, we're left with the language where we chop off that given string W from the strings in the language L. Now our question becomes, if we have a DFA for a regular language and these sets A and B, can we check if A and B cover L in polynomial time? And our answer here is yes. Let's look at the algorithm that allows us to do this. We'll start off by constructing a DFA M that recognizes the set difference of L and our set A. Then for every string in B, we're going to run the machine and keep track of the states that the machine ends in. We'll call these Q-marked. Then we're going to search for all paths from the start state to all of the accepting states. If we find any path that does not contain a state from our Q-marked, then AB does not cover L. Otherwise, we know that A and B do cover L. Now, given a prefix grammar, can we check if the language is sigma star in polynomial time? And again, we can. If we take a look at this, we're going to define these sets A and B, where we have our rules given in the usual way, where we have a non-terminal and all of the rules. And so A will be these rules here, and our set B will be rules of the format given here. And we'll have these defined for each non-terminal in our right linear grammar. So because we showed that prefix grammar can generate an equivalent right linear grammar using the Fraser-Page algorithm, we can go ahead and generate the right linear grammar when we need. And so here we'll take these two claims combined with the previous algorithm we saw for checking if A and B cover a language to check if a prefix grammar generates sigma star in polynomial time. Up next, we'll be looking at the restricted equivalence problem. Here, our input is a DFA and a prefix grammar, and our question is, are the languages of the two the same? Unfortunately, because we can reduce the problem from this problem, we will not have polynomial time anymore. We can ask the same question if we have a set of DFAs. Can we check if the union of those machines, languages, is sigma star? And the way that we can do this is by introducing a new alphabet where we have this new symbol, C, and then C1 through CK. And we construct the DFA for the regular language given here in polynomial time. Then, for each DFA, we construct a prefix grammar. This can be done using Ravi Kumar and Kwan's algorithm proposed in their unfinished work. Then, what we can do is form this new prefix grammar where we take our new alphabet, S prime, which is the union of our base strings from all the other prefix grammars in this step, and P prime, which is the union of all the productions. And then we can conclude that the restricted equivalence problem is P space hard because we've reduced it to the second problem proposed. The next thing we want to look at is determinism. So we need to define what does it mean for a prefix grammar to be deterministic. Here, it means that at each step in the derivation, only one rule is applicable. Let's see two examples. In this first one, it is deterministic, and in the second one, we do not have determinism because if we take the base string AA, we can apply either rule 1 or rule 2. And so what we need to do is say, can we check if a prefix grammar is deterministic in polynomial time? And here the answer is yes. So what it boils down to is checking if if we have two left-hand sides, if one is a prefix of the other, and if that larger left-hand side is productive or non-empty. And so we can do that in polynomial time. Our next question is looking at ambiguity. So here we'll go ahead and define it first. So a prefix grammar is unambiguous if each string is uniquely derived. Ambiguous means that we have one string derived in two different ways. So if we look at, again, this first prefix grammar, it is unambiguous. Each string only has one derivation. And then in this second one, if we look, C is a base string, and we can also produce C by starting with the base string AA and applying this rule. So we can have C in two different ways. We also have this alternate definition of ambiguity, where if one of the following conditions holds, then we know that the prefix grammar is not ambiguous, that it is ambiguous. So here, this first part A is saying that we have one base string that can produce another base string. And that's what we saw in the previous case where we had the prefix grammar 2 that was ambiguous. The second one is saying that we have one string derived in two ways, and we're always going to look at the last step that is distinct in the derivation. And we have shown that we can check if a prefix grammar is ambiguous in polynomial time. This table here summarizes the complexity results for the problems we have just discussed: universality, ambiguity, and equivalence to a DFA, for DFA, NFA, and prefix grammar. And here, for NFA, we can also consider right linear grammar because we can easily convert from NFA to right linear grammar. And we can see that for prefix grammar, we have a better time for the universality problem than NFA, but for the other two problems, we have the same complexity. So what's next for this work? Our immediate next step is to look at Shiller-Greibach's definitions. She gives us these two definitions for tau and beta, and they are related to the matching problem. We're particularly interested in this because we can take our prefix grammar definition, and then we have that the language of our prefix grammar is the same as tau when we replace our definitions into hers. And then we can also have it equivalent to the definition for beta, where we consider the productions in reverse order. Our question would be, can we get right linear grammars in polynomial time for these? Another next step would be to treat the prefix rewriting system as ground term rewriting systems, where each symbol is a monadic function, and then look at unification and other related problems. Thank you very much.